This week we're very happy to have Carl Wang-Erickson from Imperial College, who will speak about derived structures on representation.
All right, thank you for the introduction and thanks for the invitation. The main point of my talk today is to just first recall the deformation theory of representations, and then just show that if we ask some very natural questions about deforming representations, we'll arrive at structures that form what can be legitimately called a derived deformation ring. So it's sort of to arrive at derived things as classically as possible. So let's start out with classical stuff about deforming representations. I'm just going to focus on cases of interest in number theory, so representations of G being a profinite group. I might want to satisfy some reasonable and common finiteness condition. And then throughout today, I'll fix in each situation, there'll be a fixed residual representation of some finite dimension, where F is some finite field of characteristic P. Now, I'm going to consider deformations with associative coefficients, so it might be better to just, when it's convenient, actually most of the time, I think I'll think of it as a representation of the group algebra into D by D matrices. Okay, so we'd like to deform this. Let's just, the categories of rings that I'd like to deform to are, today they're going to be A, and these are going to be augmented F algebras, meaning that I have these maps of F algebras, but also it's Artin and local. And then there'll be a few situations where I want to consider commutative deformation rings, which are algebras over the p-typical Witt vectors here. So these are again, local with this residue field map. Artin, local. And maybe I'll write CF. as the F algebras among these. All right, so I'm going to talk about lifts and deformations. So a lift, always of rho to A, is some rho A. What's C? What's this? CF. Oh, it's just the F algebras among these. Yeah, so it's the characteristic P ones of these. Yeah.
Those ones are associative, but not necessarily commutative.
Yeah. Oh, I should say commutative. Yeah. Yeah. C is commutative. Okay. So in particular, like if this makes you uncomfortable being an associative ring, you can just think of it as a tensor product of rings. Okay, and then we want, I'm always going to let MA be the maximal ideal.
Can you have the power series commute with base change in this situation?
Power series.
I mean, you're taking a sort of
I should just say this. I don't want
It
to
doesn't always commute with base change, right?
base change like so. Oh, right. Yeah, but these are Artin. These are Artin. So
Yeah, that might be fine.
I don't want to. There's some way to resolve this, even if not. So mod MA is equal to rho, and then deformations are equivalence classes of lifts under inner automorphisms on the target. Okay. Now, although there's certainly cases of interest where it's not true, all the structures of interest will be evident when that I want to talk about when rho is absolutely irreducible, and then we can quite easily produce a universal deformation ring. And I'm going to focus on the associative case. And what would this be? One can readily, it's just a ring that's, you can take the completion of this associative algebra at the kernel of rho. Okay, so this is a local ring. And it'll be Morita equivalent to the universal deformation ring. So this is the universal deformation ring. And you can, non-canonically, draw such an endomorphism. So you can choose an idempotent in here and take the multiply on both sides by that idempotent, and you get the universal deformation ring. So it's not that the construction of this is very easy. So what do I mean by universal? I just mean that Hams, and I guess you could say pro represents it. Defs 2 A. Okay. All right. Now, we'd like to understand how to compute this in terms of cohomology. So the main object that appears here is to understand it using group homology. So today C is going to be a complex, and it's the complex of continuous cochains. I should say rho is continuous. I'm always just assuming continuity. All right, so this is inhomogeneous group cochains. These are just simply functions from in degree I. Are functions from I copies or dot copies of G to here with the usual differential given by the adjoint action of G on this ring. Okay, and then I'll use usual notation for co-cycles and co-boundaries, and then we have cohomology, which I'll also write as just H, today. In each degree, like so. All right. Now, we see that this complex is useful right away. So whenever you have a function from G to here, so an element of C1, then you can set up some 2D by 2D matrix valued representation. And this will be a lift to the ring of dual numbers if and only if it satisfies the co-cycle condition. So if and only if it lands in actually, if and only if it's in Z1. And then when we start looking into deformations, we realize that conjugating by any matrix that's 1 plus some matrix times epsilon, so that you could think of there sort of being a epsilon in here. So conjugating by any matrix that's 1 plus something divisible by epsilon, what you then get is you calculate the tangent space to the deformation functor. So let's write R rho contains M rho for its maximal ideal. And I'll express it actually in terms of the cotangent space. There's a canonical isomorphism with H1 dual. So today, I'm going to have star be linear duals, and I'm going to reserve dot for complexes. OK? So this then gives us that the free completed tensor algebra admits a surjection onto R rho. So this, I just mean the non-commutative power series ring on this vector space. Dualed, surjects onto R rho. This is highly non-canonical. I might just want it to commute with the projection to here. OK, natural map here under that isomorphism. OK, now once we've set up this, we can then talk about finding obstructions. Basically asking, what is the kernel of this surjection? Okay. This will tell us when we have some deformation to some quotient of here, say, to some ring, when can it not be lifted or not. So what we can do to compute this is that there's actually, let's use M for a moment to denote its maximal ideal. There is, a canonical surjection onto J mod Mj. So in particular, for example, the dimension of this vector space, I'm thinking of all these as finite dimensional in each degree, gives us a bound on the number of generators of the quotient ideal here. Bound on the number of generators of J. So how do we produce this? This comes from taking the universal representation here, and then just taking any lift. So that's the universal representation, and then taking any lift to t hat h1 mod mj. So it may not be a homomorphism. And then when you just take this function and you take the function on two variables in here, such that if it satisfied it, it would be a homomorphism, you end up getting a 2 cocycle, and its cohomology class ends up being well defined. Okay. All right. Now we'd like to know then what is J. So we need to use more about the DG this algebra here. So I said algebra. It's not just a complex. It has a multiplication operation. So it's the graded multiplication on C dot. All right, so Ci is functions on I copies of G. Here's functions on J copies of G. Together you get a function on I plus J copies of G landing in endomorphisms tensor squared, but then you map that to endomorphisms using the fact that endomorphisms is a matrix algebra, and we multiply them. OK. And then it's an exercise. This is then a DG algebra. The Leibniz rule is satisfied.
Question?
Yes?
Sorry, quick question. If that surjection there is compatible with an isomorphism, why is there going to be a kernel?
Compatible with an isomorphism. What do you want to be an isomorphism?
Sorry, you say there's an isomorphism going down to RP mod n squared.
Yeah, that's not an isomorphism, sorry. It's just the canonical map here. Thanks.
Somehow you wanted that to like match with your chosen.
Exactly. Yeah, this isomorphism defines such a map. Yeah. All right, now, OK. All right, so now an example of what we'd compute. Let me just show you an actual example from number theory that this is some joint work with Preston Wake, where we use this multiplicative structure to calculate this. So here, the version of the deformation ring that's for a certain row, and over the field FP, so its bit vectors is ZP. Let's see, is equal to T, where here G is some quotient of G. It's the quotient of the absolute Galois group of Q, where only P a prime n and infinity ramify. All right, and T is the Hecke algebra of actions on weight 2 cusp forms of prime level n, gamma naught n, that have a congruence mod P with the Eisenstein series. So this is the Hecke algebra that was studied by Maser in his Eisenstein ideal paper. And we find a Galois deformation ring with some conditions, not just representations of the group, but there's some conditions on it, that's isomorphic to T. OK. And this allows us to answer some question of Maser, which is how many cusp forms are there here, or what's the ZP rank of this module? How many cusp forms are congruent to the Eisenstein series? This is just one less than the rank of this Hecke algebra, so I'll ask what is the rank as a free ZP module of this Hecke algebra. Well, Maser also proved that T is singly generated as an algebra over ZP. OK, and then this means, since we know everything is free over ZP, to compute this, we would just like to find mod P. So we just want to find the abelianization of the deformation ring that I've been talking about. And we know from Maser, if we know an isomorphism, that this just looks like this ring. So what's implicit here then is that there's a single cohomology class. So I'm writing F to say that it satisfies some conditions that are like analogs of crystalline conditions for some representation rho that happens to be two-dimensional. And right. Now Maser came up with a criterion for this ring to be for this ring to be, for there to be some cusp form congruent to the Eisenstein series. But he's asking for the rank. So we're interested in finding a deformation to fp x mod x cubed. So a second order deformation, let's call it. Now taking a basis using epsilon and epsilon squared in 1, this two-dimensional representation over here looks like a six-dimensional representation over f, and that's what I'm writing out here. And this is a homomorphism. The condition ends up being that df2, thinking of f2 as an element of C1, that differential is equal to E cup E, where I've taken E in Z1 to be some cocycle inducing this cohomology class. Okay. So then what this says is that, so then we find that there exists such an F2 if and only if E bar cup E bar is 0 as an element of H2. Okay. This cup product being a condition to, as determining whether a first order deformation coming from E extends to a second order deformation. This was noted by Maser in his deforming Galois representations paper. We need a little bit more complicated product if we want to see if this extends to a third order deformation. So here now we want something like this. Okay, so here we're trying to see if we can find some F3 making this a homomorphism. So this would give us a third order deformation. Okay. We need there to exist an F3. And the condition ends up being that dF3 is equal to E cup F2 plus F2 cup E. Okay, and this is an instance of a representative of a triple Massey product of E. So without getting into, so there exists such a thing if and only if a triple Massey product or a certain element of it, E bar, really a triple Massey power, vanishes. That's just terminology for this being a 2 coboundary. It's automatically a 2 cocycle. Okay, so the theorem that Preston and I prove is that this G, or the rank, is determined by these Massey powers of E. Okay. Now we would like to, so in particular, we've found a J in this case. J is, well, we're trying to find what that number, where to go. G is up here, and that determines J. Okay. Now Massey products involve a lot of choices. Every time that I choose an F2 or F3, it's the property that restricts my choice is what its boundary is. So in particular, there's flexibility in the choice of F2 or F3 up to cocycle. And that does matter when you actually make these computations. But it shouldn't really matter if we choose things systematically. So the next idea I want to introduce is that A-infinity algebra structures systematize this these systematize this finding deformations or computing obstructions. Okay, so to start this off, I want to introduce an equation that, well, basically first discussing lifts. So C star determines lifts. Sorry, the cochain complex. This DG algebra determines lifts in the following sense. the perspective I'm going to promote here is that C, as well as its cohomology, C being a DG algebra, its cohomology being an A infinity algebra, are themselves deformation rings. And the way that they're related to deformations is the so-called Maurer-Cartan equation, or Maurer-Cartan functor. So a Maurer-Cartan element of C in A being one of our test rings again, written like this. Well, I'm going to write them as C and C1, tensor MA. So you can think of this as a function from the group to the endomorphism algebra tensor, the maximal ideal, such that dc plus the cup product equals 0. So here what I'm doing is that, to interpret this formula, we know that C is a DG algebra, but I'm just extending this DG algebra structure to the tensor product by just having the differential act as 1 here. So differential tensor 1 is this differential, and then taking the product just coordinate-wise. OK, and then it's a quick exercise that if you have some C in here, that C is Maurer-Cartan if and only if rho plus rho C, which is a function from G to MdA, or A, can extend it to AG, is a homomorphism. Okay, so this is just like the equation here, but when you get the actual multiplication in A involved, you can stick with that equation. Obviously, you couldn't stick with anything like that equation when you didn't allow yourselves for the coefficients for the third order deformation. Right. Yeah, what you'll find is that if you write out, again, the condition for this to be a homomorphism as a function on two elements of G, then you'll get exactly this 2 cochain, and it needs to vanish for it to be a homomorphism. Let's see. All right.
And what do you mean by rho psi? Is it a product or composition, or what's the sort of?
Yeah, it's a product. So when you evaluate it on gamma, it would be rho of gamma times C of gamma. Yeah. So, all right, now we want to encode conjugation on these Maurer-Cartan elements, and this just going to introduce terminology for this. So, in fact, they're just within this generality, of course, if it doesn't have anything to do with representations, there's a gauge action. Of C0 tensor MA. So this is just matrices valued in the maximal ideal on that preserves the Maurer-Cartan. So let's just say X is an element of this tensor product. And in the representation case, it is simply conjugation by 1 plus X. Okay, this being an element of the matrix algebra. Okay, so this gauge action is exactly the inner automorphism. So this gauge equivalence classes are conjugation equivalence classes or deformations. All right, and so let's just write MC bar for gauge equivalence classes. Okay, so C is the object that's really associated with lifts via the Maurer-Cartan functor. Gauge equivalence classes are deformations. to actually compute this, we'd like to directly relate h to it. So h. Next, we want to relate h determines deformations. Okay, now we've seen that h itself gives the tangent space. It gives us sort of first order deformations. So if we take some xi bar in h1 tensor MA, and we tried to use this original more Cartan equation, well, we're in H, so it has the graded product induced by the graded product on C, but the differential is 0. It turns out that this cup product vanishing in H2 tensor MA is the right condition for determining lifts, for deformation, for determining whether this determines a deformation, if it only lasts so long, if the maximal ideal cubed is 0. So cup products are good for determining second order deformations, but no more, as we saw. So we need some sort of different algebra structure here, and this is an A-infinity algebra structure. So an A-infinity algebra structure on a graded vector space, so I'll just take H because that's the one we're going to be interested in, is a sequence of maps. I'll use M for this collection. From the nth tensor power of this graded vector space to itself that has homogeneous degree 2 minus n, and some conditions. And I'm not going to write down explicitly here, but I will write them down in an equivalent form in a second. And then a morphism, infinity morphism. From H with an A-infinity structure M as above, so this will be notation for A-infinity algebra, H with its M, to say H prime M prime, is another integer indexed collection, is so this had graded degree 2 minus n, and this one is degree 1 minus n. Okay. Again with conditions. That's right. Yeah. So we will want to add this data in a compatible way with it being a graded algebra in a second. But an infinity algebra is a graded vector space with this structure. Okay, to say what these conditions are, as well as to relate these to deformation rings, something called the bar construction is quite useful. I'll present a dualized version of it. So we want to start with an A-infinity algebra. Okay, so first, right, we have our MNs for each n. And what we want to do with these is first take the suspension, shift the complex. Since this is degree 2 minus n, if you keep track of what's happening with the tensor powers, this now ends up being degree 1. Then I want to take the duals, suspend first, then take the duals, but I'll write it like this. Oh, wrong way around. There we go. Okay, I'm reserving star for linear dual. This is what I'll write mn star when needed. Then I want to take the product on the codomains. And then finally, this lands inside of the free tensor algebra on the graded vector space. It's in the maximal ideal, that free completed tensor algebra. And then I just extend it using the Leibniz rule. So then I get what I'll call m star. Okay, so now we have some map that has degree 1 that satisfies the Leibniz rule by construction. So it's a derivation. And then the fact is that M is an infinity structure if and only if this derivation is actually a differential. In other words, if and only if this is a DG algebra. All right, so there's lots of conditions, and they do have natural meaning. That's quite important, but this is what I'm going to stick with and emphasize today. And in terms of the conditioned on morphisms, I'll say that, furthermore, the sort of undualized, like if you never take a dual here, the undualized version gives you an isomorphism of categories. So you can, in other words, the morphisms are completely preserved. An A infinity morphism so I guess co-complete, co-free, co-DGAs. And this is just a dualized version of it. And this dualized version makes good sense as long as H is locally finite, as long as each A is finite dimensional. And that's something that I want to assume today using a finiteness condition on G. Need be. Right, so morphisms between these DG algebras are exactly the same as A infinity morphisms. So as an example, a DG algebra like C today. So let's just use C with its differential and is an A infinity algebra with M1 being D, right? It has degree 1, M2 being the product, graded degree 0, and Mn is 0 for all higher n's. So for this reason, we call these Mn's higher multiplications. And yeah. All right. Now the next important theorem is that there are many A infinity structures on H that do not forget the information of C. While we saw from the little product computation here that H loses too much information if you only remember its graded algebra structure. There we go. So in this form, this theorem is due to Kadej-Feely. So let's take C to be a DG algebra. Since I'll just keep using this to denote the product on it, since that's what's been happening today. So there exists an A infinity algebra structure on its cohomology. Algebra structure M on H. And F from HM to C, an A infinity morphism. And here I am right away using the trivial A infinity structure on this DG algebra with the properties that M1 is 0, M2 is equal to the original product mod boundaries. So this is to Preston's question. This A infinity structure on H extends the graded algebra structure on the cohomology induced by the product on differential graded algebra. And where F1, H to C, and I should say that one of the conditions on F1 itself is that it's a morphism of complexes. Okay, is a lift of cohomology classes to cocycles. Of the standard map from cocycles to cohomology. And I should say,
What if these projections don't split? Can't that happen?
which surjections?
From Z to H. If they don't have a
Yeah, these are just over fields. They're vector spaces. You can split them. Yeah.
so there's some finite dimensionality assumptions or something. At least it's over field.
Yeah, just over a field. Yeah, it's certainly, yeah, there's definitely lots of other concerns when you're not working over a field. Okay. All right, and then I'll just say in words that these structures of M and F together are unique up to non-unique isomorphism. And maybe I'll just make this remark that there exists straightforward formulas for M and F in terms of, if you choose, like you're saying, some splitting here, just choosing some way to write C dot as boundaries plus a lift of cohomology. So together these are Z. And then some complement, L for lifts. So you want D to map this isomorphically onto B dot plus 1. This splitting ends up giving you enough information to induce all these data. So they're highly non-canonical, but they can be induced by something pretty simple. All right, so as an example, so this choice, for example, gives you Mn. So if you start with n elements of H1, the nth product structure, under some conditions such that a Massey product on those n elements even makes sense, lands in H2 because its graded degree 2 minus n is a Massey product. Or is an element in a Massey product. I haven't given the full definition. So when Massey product makes sense on an n tuple here, this will give you an element of the Massey product. All right. Let's see. Also state the right generalization of the Morikawa-Tan equation to this setting. So the Morikawa-Tan equation for H. H and A is A being one of our test rings again, I should say H is an infinity algebra. Again, elements are I guess I'll use ends. Okay, so all of these, again, you just extend each mn product to actually make this an A infinity algebra where you just take the multiplication in this coordinate and you take the A infinity structure on this coordinate. So this will end up being a element of H2 tensor MA, and this is a finite sum because I'm always taking art in algebras. Okay, and then it's so this might be known as the homotopy Mohr-Cartan equation. Right, and it's a theorem of Kontsevich, although he's probably working with Lie analogs of A infinity algebras over C, but the idea is the same. All right, and then, sorry, something to say first. Is that there exists a gauge action of H naught tensor MA on MC. HA. Okay. And then you get gauge equivalence classes. Gauge equivalence classes. Are a quasi isomorphism invariant on HM. So an A infinity morphism is a quasi isomorphism. I guess did I erase it? Yeah. When F1, so there's one over here, is actually a quasi isomorphism. So an A infinity quasi isomorphism is defined as just F1 out of the entire collection of Fs being a quasi isomorphism. So in particular, this is a quasi isomorphism. And the idea here is that this gauge action in this case of a residually irreducible representation is trivial. It's just the scalars. Yeah, invariant on HM, sorry. All right. So in particular, by this Kadeshvili's theorem that gives this quasi-isomorphism, we get we have a quasi-isomorphism from H to C, and this induces MC HM. Gauge equivalence classes here are isomorphic to gauge equivalence classes here. Okay. And then another final fact before I can get to the Upschotten theorem is that this can just be checked with a computation, is that the definition of a Mohr-Cartan element, which by the way is consistent between the DG case where it was differential plus product, is 0. You need to take this to the tensor power n. Right, so this Mohr-Cartan equation reduces to the homotopy Mohr-Cartan equation. It reduces to the DG algebra Mohr-Cartan equation. Is that MCH is equal to Homs as DG algebras from this this dualized bar construction. Let's call this bar star HM. Okay. So this collection here of this free graded algebra with this differential is a definition of bar star. Just using, just something you can compute quite readily. And now we can take, here I'm considering this classical Artin algebra to just be embedded as a DG algebra in degree 0 with trivial differential. And now let's compute what this is. So we want to find what is a map from here to A that computes with the trivial differential. So first of all, it's got to factor through the portion of this graded of this graded vector space that's in degree 0, and that's the H1 portion. The suspension moved H1 into degree 0, so it's got to factor through here. And then we produced m star using the Leibniz rule, extending it from something defined here. So it turns out that you just have a Hom of usual algebras modulo m star restricted to H2, because H2 dual is the stuff that's lying in graded degree -1. Right, so the A infinity algebra structure is enough choices which is a lot of choices, to actually give you a presentation of the deformation ring, it turns out. So this computation gives you the theorem. That a choice of M and F, as in Kardashvili's theorem, which comes from a much simpler choice of decomposition of the cochains, induces an isomorphism from this complete associative algebra to the deformation ring. And if you tensor this up with the endomorphism algebra, you get the original group algebra completed at the kernel of a row. Okay. Main idea here is that we know that the Mora-Cartan elements of C up to gauge equivalence is exactly deformations. And then that's the same as Mora-Cartan elements here. But then the gauge action, assuming that rho is irreducible, this gauge action of H naught is essentially trivial. It's just inner automorphisms. All right, so how can we use this for some applications? All right, so a few comments on this, right? First, this is due to Segal when in characteristic 0, there are more things to work out in the gauge action in general. Also, here you could say we have this bigger and naturally existing deformation ring that when you restrict it to its, what you could call the classical hole, sort of the adjoint functor to the inclusion from algebras to DG algebras, that's what it does to this. Well, this is hopefully then a derived deformation ring. And I'm not going to talk about actually producing a notion of derived deformation and derived deformation functor. But over C and in characteristic 0, there's a paper of Kapranov that presents this very nicely. So I'm not going to talk about actual derived deformations today. But the idea is that this would be a derived deformation ring, this DG algebra. OK. So I'll conclude with some applications. one is smooth representations of G over F. So the idea here is that G could be, G is going to be a p-adic Lie group for this discussion. And we're interested in its smooth representations. There's a Prandtl eigenduality with profinite, basically profinite modules. Profinite modules for Fg. Let's just assume that this is pro-p, torsion-free for this discussion. So whenever we have this setting, and perhaps we have a subgroup here, we can produce a derived Hecke algebra, which whose modules are related to these smooth representations. I'm going to reduce to the case where this involves a choice of a subgroup. I'm just going to reduce to the case that I equals G. So the derived Hecke algebra with this reduction, which doesn't end up being fundamental in any way, is X'd in this category of smooth G representations, of a trivial representation, which is a graded algebra. And it's isomorphic as a graded algebra to the opposite algebra of the H dot that we've been talking about today. So Sorensen very recently posted a preprint that talks about the A infinity structure on this derived Hecke algebra and what it determines about the category of representations, really the derived category. So this is not the full scope of his paper, but just as an example of what he proves, he uses the H and M as above, meaning what we've been discussing today, which extends the graded algebra action here and gives us an A infinity structure on these. G is abelian, so some number of copies of ZP implies that M is trivial. In other words, only M2 is not equal to 0. It's a property known as a formality, and he asked some questions. Is the converse true? And secondly, does the derived Hecke algebra with its A infinity structure determine the Iwasawa algebra? And it's a corollary of this theorem here that the answer to both of these is yes. I think it's very nice to see an example of what's happening in the abelian case under some pretty mild assumption on G that it's equi-p-valued, there's a Lie algebra. So this is due to Lazard. But the Yoneda algebra, so isomorphic has a graded algebra to an exterior algebra on the dual of an abelian Lie algebra concentrated in degree 1. Okay. And that's just C. So if we assume that the A infinity algebra structure is trivial, what presentation do we get? Right? So I should say in this case, R rho, because rho is one-dimensional, is isomorphic to Fg. Because G is pro P, the only simple representation is the same as taking the kernel of the trivial representation, which we're writing as F over there. OK, so what exactly is the presentation there? You get T hat of G over M2 star is the only non-trivial presentation. And what you get here is exactly the alternating tensors in degree 2. So then you just get a commutative power series ring, which is exactly what you'd expect. So this is, that's right, it's sim hat. Since I'm out of time, I'll just give the other example I had in mind in words and write a little bit about the construction. So as another example, which is really quite different, which is why I'll call it section 4. So here we are interested in crystalline representations of GQ, absolute Galois group ramified only at P and infinity, so crystalline at P. And what I can produce is a DG algebra contained inside the usual algebra, which is the right DG algebra to determine crystalline deformations of this. So this, what you get, the cohomology you would expect from this, so the cohomology being H1f, HNF, you expect from the Bloch-Kato conjecture that H1f is 0 and that H2f has dimension d minus 1 over 2, which in this setting is known as the L naught invariant. OK, so because H1f is 0, the classical deformation ring is 0. You can sort of, it's possible to ignore H not F. I'm going to think of this as crystalline and irreducible. So the crystalline deformation ring of this row is just QP. But then what do we get out of the derived one? Well, H2 is the only non-trivial contribution, so you get this, and which is actually a dual Semler group, or it's dual to a dual Semler group. And when you take its commutative version, you take the symmetric quotient of this. Because this is in, the sigma, we take something in degree 2, move it to degree 1. The right commutative quotient is an exterior algebra. And this is an exterior algebra that's appeared as a derived deformation ring in some works of Galatius, Venkatesh, Hansen and Thorne, and Venkatesh. All right, thank you, that's all.
Are there any questions?
Yeah, I just have a notational question.
Mhm.
What does this HIF stand for?
It stands for Bloch-Kato-Selmer groups. So I'm just trying to invoke H1, G, and rho, cohomology of the adjoint representation. But then I want to have some condition on it that cuts out the crystalline condition, deforming these global Galois representations. And now I'm just writing that as F.
So there's only a condition at P. Or is there a condition everywhere?
There's a condition everywhere because I've disallowed ramification at all places except P by starting with this global Galois group in the first place.
Unramified conditions as
Yes.
yeah, okay.
Just for some, yeah.
I missed what you said at the end here, that you took this, so this bar of HF is your version of derived deformation ring, and what does it say in the sign? Sim?
Yeah. So really, this should be the right derived deformation ring if you worked in an associative setting. And now it's conceivable that this should exist because, crystalline condition is stable under tensor products, and there should sort of be some Hopf algebra whose reps are crystalline reps of this. But we usually want to consider deformation rings with commutative coefficients. And the analog of abelianizing for something that's a free tensor algebra generated in graded degree 1, well, then you just get the skew symmetric quotient, because that's what it means to be graded commutative, generated in an odd degree. So you get this.
So like if you restrict the deformation functor to a commutative test object,
Yeah.
it would factor through that.
Yeah. So commutative DG algebras. We're in characteristic 0, so that should be OK.